All right, so next we have electrons passing through a resistor. Arrow shows the direction in which the electrons are moving. I'll underline that. If this was a test question, I would make sure to bold that. Although this wouldn't be a test question because I never have there could be more than one correct choice as test questions. So what is correct? So the fact that we have been given the direction of the flow of electrons is confusing, and I don't want to deal with it. So what I am going to do is say, yes, that is the direction of the flow of electrons, but everything that I have remembered is more straightforward if I talk about the flow of positive charge, and that is also what we call current. So if the electrons are going to the right, the current is going to the left. So I'm just going to draw that there, and I'm going to ignore this because there's a lot of kind of double negative type thinking here with the electrons. I know that current flow of positive charge, everything makes sense when we think about positive charge with things rolling downhill in the way that's analogous to gravity, so that's what I'm going to do. So I have current going to the left. Okay, so first, the electrons are moving slower at point A than point B. I like the water pipe analogy for this. There's no way, if something slowed down as it moved through the resistor, then if you think about water going through a pipe, if it slows down as it moves through the pipe, but the pipe doesn't get bigger or smaller, then your pipe's going to explode somewhere. That just can't happen. You have to have the same amount of water coming in as you have going out. The same is true for electrons and current flowing through a wire. So this one can't be true. Next, electric potential is higher at point B than point A. Well, I have current, the flow of positive charge, going from B to A. I know that positive charges roll downhill from high potential to low potential. So that fits with what I want to do. So that one's true. Electrons are losing potential energy as they move through the resistor from A to B. Okay, so as electrons move to the right, again, let's just think about this as being current to the left. So as the current flows to the left, that's rolling down the hill. It's doing what it wants to do. So rolling down the hill is should be losing potential energy and speeding up as it does. So this is also true. I guess if we were running to think about the flow of electrons here rather than the flow of positive current, it still works because we know that electrons, negative test charges, want to roll uphill, so they want to go from low potential to high potential, which we know that it is, right? A is a low potential, B is a high potential. We already said that that's true, right? B is high, A is low. So electrons want to roll up the hill, and they will speed up as they do. As they gain their kinetic energy, they're going to lose the potential energy. So that one is D. And I just kind of realized the way that we talk about this is kind of violates what I said in A. Electrons are moving slower at point B than they are in point A. So the electrons are moving the same speed. There's no way for them to speed up. So as the electrons move through this resistor, they're still losing potential energy, but they're actually not gaining kinetic energy. What the kind of energy that is happening is that energy, potential energy, electric potential energy, is being converted into heat. So the resistor is warming up a little bit as the electrons go through here. So they're losing their potential energy, but it's not causing the electrons to speed up. It's causing that potential energy to turn into heat. And E, potential is lower at B than A. That's the opposite of B. So we already said that B is true, so E can't be true. So B, C, and D are all right there. And next is the length of a certain wire is kept the same while its radius is doubled. What is the new resistance of this wire? So this is a factor type question. This is another kind of, I tend to put one factor style question on every test. So you should probably expect to see something, not necessarily this question, but something that asks by what factor has something changed. So we have length of the wire, radius of the wire, and we're looking for the resistance of something. And we are not changing the material. Um, and so the equation that goes on this is radius. It depends on the resistivity, so that's a property of the material. That won't change, times the length of the wire divided by the area of the wire. So that's not going to change, and length is not going to change, and area is going to change by way of doubling the radius. So I want to get rid of area here. There's a wire, so I'm just going to assume that it's a circle. That's a pretty fair assumption. This is going to be resistivity times length over pi r squared. Okay, so I'm going to write this in ones and twos. So I'm going to say that the one subscript is what it was before the radius was doubled. I don't really care about the resistivity and the length, since those are not things that are going to change, so I'm not even going to bother giving them subscripts. If you don't like working in letters, you're welcome to put a 1 in there for both of those right now if you want. You can actually put a 1 in for all of these things if you want. I'm going to do this with letters, but if putting 1s instead of letters works for you better, then that's fine by me. All right, so in the second scenario, so for my resistance in the second wire, I need to double the radius. So I have rho, radius 2 is going to be rho L over pi, radius 2 squared. But I know that this number is twice as big as that number is. So let's plug that in, rho L over pi times twice the radius of the first one squared. Now let's pull out this 2, which is squared. So 2 squared is 4. So 1 divided by 2 squared times rho L over pi r1 squared. So that's 1/4 what it was before. So rho L over pi r1 squared, rho L over pi r1 squared. This is just the initial radius. So, or I said radius. This is just the initial resistance. Big R here is resistance. Little r here is radius. And rho, which is kind of like a Greek R, is the resistivity. That's just a property of the material. So our resistance is reduced by a factor of 4. It's 1/4 as big. It's reduced by a factor of 4. When you're doing problems like this, a great way to check yourself is to think about whether or not that makes sense. Okay, so I have 2s, 4s, and 8s here. I'm doubling something, and the thing that I am doubling has a square in the equation. So probably I'm going to have a 4 would be the first thing that I would say in here, because if I double something, I'm going to end up with a 2 squared in this equation where my radius is. So immediately just looking at this and knowing what formula I'm looking at, I've narrowed it down to A and E. Next is physically, length of a wire is kept the same while its radius is doubled. So if I go to the analogy of water going through a water pipe, I can fit a lot more water through a bigger radius pipe. So resistance is the resistance to flow of electrons, just like the water pipe. The bigger water pipe will have more water flowing through it. By that analogy, the bigger water pipe has a smaller resistance. The same thing works here. So I have that bigger wire has less resistance. So I should expect that doubling the radius lowers the resistance. Okay, so without doing all of this, I could probably just pick that this one had to be the one. It's good to do it both ways to kind of see that it makes sense, but good that every